Hi guys, this is the challenge question walkthrough for Edexcel's Pure Year 2 textbook, and today we'll be going through review exercise 3. Okay, our first question. The curve C has implicit equation ay plus x squared plus 4xy is equal to y squared. And for part A, find in terms of A where necessary the coordinates of the points such that dy. So here we can use implicit differentiation. So if we differentiate both sides, so differentiating ay, we get a dy by dx plus 2x plus, now we're going to use the product rule, so we have 4x times the derivative of y, dy by dx, plus y times the derivative of 4x, which is just 4, and that is equal to 2y times the derivative of y using the chain rule, dy by dx. Now if we collect all terms with dy by dx onto one side, so if we collect them onto the left hand side, we have 2y minus 4x minus a dy by dx is equal to 2x plus 4y. And therefore we have dy by dx is equal to 2x plus 4y over 2y minus 4x minus a. And therefore we have that 2x plus 4y must equal 0. And therefore we have x is equal to minus 2y. And we can substitute this into the original equation. So we have ay plus x squared, which is minus 2y squared, so plus 4y squared, plus 4xy, so minus 8y squared, is equal to y squared. Taking all the terms onto the right hand side, we get 5y squared minus ay is equal to 0. Now factorising, we get y times 5y minus a is equal to 0. So we get two solutions for y, y equals 0 and y equals a over 5. And using x equals minus 2y, we get here x is equal to minus 2 times 0, so just 0. And here x equals minus 2a over 5. So therefore, for part A, the coordinates are 0, 0, and minus 2a over 5, a over 5. And for part B, we're asked to show that there does not exist a point where dx by dy equals 0. So we know what dy by dx is. That's 2x plus 4y over 2y minus 4x minus a. So we have that dx by dy is equal to 1 over dy by dx. So 2y minus 4x minus a over 2x plus 4y. And for this to be equal to 0, we now must have that 2y minus 4x minus a is equal to 0. So here we have that y is equal to 2x plus a over 2. And if we plug this into our original equation, we have that a times y, so 2x plus a over 2, plus x squared plus 4x times y. That is 8x squared plus 2ax is equal to y squared, so 2x plus a over 2 squared. And expanding brackets, we have 2ax plus a squared over 2 plus x squared plus 8x squared plus 2ax is equal to 4x squared plus 2 times 2x times a over 2. So that is 2ax plus a squared over 4. Now we can collect terms, so taking everything over to the left hand side, we have 5x squared, and then we have plus 2ax plus a squared over 4 is equal to 0. And now if we use the discriminant, we have b squared minus 4ac is equal to 2a squared minus 4 times 5 times a squared over 4. That is equal to 4a squared minus 5a squared, which is equal to minus a squared. And now, because minus a squared is less than or equal to 0 for all real a, there doesn't exist any points where 2y minus 4x minus a equals 0, and therefore there exists no points where dx by dy equals 0. And that is what we've been asked to prove. Okay, and for our last question, question 2, the diagram shows the curves y equals sine of x plus 2 and y equals cos of 2x plus 2 for 0 is less than or equal to x is less than or equal to 3 pi over 2. And we're asked to find the exact value of the total shaded area on the diagram. So I think the easiest way to do this is to split up the blue area into these 3 areas we see here. So area 1 here, area 2 here, and area 3 here. So to start off with, we need to find the points where these curves intersect, so we can find our bounds for the integrals. So to find these points of intersection, we need to set these 2 curves equal to each other. So sine of x plus 2 is equal to cos of 2x plus 2. And we can use the double angle identity for cos of 2x. Cos of 2x is equal to 1 minus 2 sine squared x. If we choose this one over 2 cos squared x minus 1, we can form a quadratic in sine of x. So we have sine of x plus 2 is equal to 1 minus 2 sine squared x plus 2. And taking everything over to the left hand side, we have 2 sine squared x plus sine x. We have 2 minus 1 minus 2, so that is minus 1 equal to 0. And we can factorise this quadratic. So we get 2 sine of x and sine of x in the brackets. And looking at this, we need to have a positive sine of x. So the minus 1 will be in here and the plus 1 over here. So from here, we have that sine of x is equal to half, or sine of x is equal to minus 1. And we can find these values of x using the graph of sine of x. So we have sine of x is equal to a half, and sine of x is equal to minus 1. And we're told this is from 0 is less than or equal to x is less than or equal to 3 pi over 2. So 3 pi over 2 is about here. So we're only interested in intersection points before this point here. And we can see we have 3 points, which lines up with the diagram. This point here is going to be pi over 6. This point here is going to be 5 pi over 6. And this point here is 3 pi over 2. So if we first find the area 1, this will be the integral from 0 to pi over 6. And because here the cos graph is above the sine graph, this will be equal to cos of 2x plus 2 minus sine of x plus 2. And so simplifying this, we get cos of x plus 2 minus sine of x minus 2, so the 2's cancel, and we're left with cos of 2 of x minus sine of x dx. And that is equal to a half sine of 2x plus cos of x from pi over 6 to 0. And so we get that is equal to a half sine of pi over 3 plus cos pi over 6. And then we've got minus a half sine 0 plus cos 0. And so we've got a half times root 3 over 2, so we've got root 3 over 4, plus cos of pi over 6, which is root 3 over 2. And then we've got minus a half sine of 0, which is 0, plus cos of 0, which is 1. And so we get 3 root 3 over 4 minus 1. So that is the area of region 1. And to find the area of the second region, if I do that in red, that is equal to the integral from pi over 6 to 5 pi over 6. This time the sine graph is above the cos graph, so we're doing sine of x plus 2 minus cos of 2x plus 2. So that gives us sine of x minus cos of 2x dx, and this is equal to minus cos of x minus a half sine of 2x. And we're evaluating this from pi over 6 to 5 pi over 6. And that is equal to, so first of all we have minus cos of 5 pi over 6 minus a half sine of 5 pi over 3 minus cos of pi over 6 minus a half sine of pi over 3. Now this bracket here is the same as the bracket we had over here, but negative. So instead of 3 root 3 over 4, instead we'll have minus 3 root 3 over 4. And this other bracket, if we pop that into our calculator, and that gives you 3 root 3 over 4. And so we've got this is equal to 3 root 3 over 4 minus 3 root 3 over 4, so plus 3 root 3 over 4, and that's equal to 3 root 3 over 2. And finally, doing the same for the last area, area 3. So remembering the points of intersection, so this here was pi over 6, this is 5 pi over 6, and this here was 3 pi over 2. So this time we're integrating from 5 pi over 6 to 3 pi over 2. And this time the cos graph is on top of the sine graph, so we'll have exactly the same as in the first integral. So cos of 2x minus sine x dx. So integrating this, we'll have the exact same, a half sine of 2x plus cos x from 5 pi over 6 to 3 pi over 2. And this is equal to a half sine of 3 pi plus cos of 3 pi over 2 minus a half sine of 5 pi over 3 plus cos of 5 pi over 6. And once again, we can see this bracket here, and we know this bracket was equal to 3 root 3 over 4. So here, this will equal 3 root 3 over 4, but negated. And we know that sine of 3 pi is equal to 0, so this term cancels out. And cos of 3 pi over 2 is also 0. So we're just left with our 3 root 3 over 4. And so, adding all these areas together, a1 plus a2 plus a3 is equal to 3 root 3 over 4 minus 1, and then plus 3 root 3 over 2, and then plus 3 root 3 over 4. So we're left with 3 root 3 minus 1, and that is our final answer. And this lovely integration question brings us to the end of review exercise 3. I hope you enjoyed this video, and I'll see you in the next one.